Hello students, let's continue our discussion. So we were discussing about the draft tube. So as I have mentioned in previous videos that draft tube is a tube either in is a conical shaped or an elbow shape that is connected to the exit of the turbine to the tail race tunnel, right? Tail race. So tail race is a channel that uh, uh, directs the flow from the powerhouse to the outside where stream or where it connects to the main stream or the river. Okay, so this tube is known as the draft tube, and its main function is to convert the kinetic energy at the runner outlet to the pressure energy at the draft tube outlet. So as you know, the water is when water is moving from here, and it is a these turbines, especially the reaction turbine, the work is done by the pressure gradient, meaning the pressure difference in inlet and outlet of the runner, right? So when water moves here, water still possesses high kinetic energy, meaning all the energy that was possessed by the liquid or the flowing fluid is not converted into useful work. The energy is still in terms of kinetic energy. So the function of the draft tube is it converts that kinetic energy into static pressure energy at the outlet of the draft tube. So here is one example of a straight divergent tube. Okay, there is a Kaplan turbine, and this is the conical shaped draft tube, and here this is the elbow shaped, where inlet section it has a circular section and outlet it has a rectangular section. So there are other types also, but it's let's discuss only this two. Okay, now let's try to define some of the terms and also discuss about the efficiency of the draft tube. Okay, so here there is a section of a Francis turbine. There is a turbine here. This is the spiral casing from where water will be flowing. So from the section I can make it out that water must be going from this direction and it is coming out from this direction. So the section here, cross section here, is larger and this side is smaller, meaning water is already getting into the turbine. That's why the quantity of water flowing through this is less. That's why this section is also as reduced here. So after it after it does some work on the runner, and it comes out from the this portion, right, at the exit. So since it is the mixed flow type, it enters radially, it comes out axially. So it comes out, and to connect the exit of a runner to the tail race, there is a tube, that is the draft tube. So let's consider the the inlet section as the section 1, water inlet section to the turbine as section 1, outlet section to be section 2, which is situated at the level Z2, and this is entrance is, let's say, it is at the level Z1. Z1 and Z2 are the reduced level or the height from the datum. Okay, and the last one is the exit of the draft tube. Let's consider this to be the section 3rd, and as you have already figured it out from this figure, the draft tube is inserted into this tail race. Okay, so there is the water level, the tail race water level is up to this portion. So here the pressure is atmospheric pressure. So here I have mentioned it as atmospheric pressure, and let's say the exit and this height is h. Okay, so with this, let's analyze the system. And also okay, so I have explained everything here. All right, let's apply Bernoulli's equation, Bernoulli's principle at the outlet and this section. Okay, so here pressure head plus velocity head plus the datum head, right? Z plus h becomes the total datum, datum head or potential head. Okay, is equal to pressure at this point, pressure head plus velocity head plus Z3, right? The potential head plus HF from here to here. So we can assume that since this distance is very close or near, we can assume that The velocity is at this section and velocity at the exit section is more or less same, okay, and the frictional loss is negligible. So which gives us, if this v and v3 same, so we can strike this off, and hf is 0. That's an assumption. So from this expression we get to know that pressure at the exit equals the atmospheric pressure head at this point plus the h, right? So that is the total pressure head at the exit level. Further, applying Bernoulli's principle at the exit level and the exit of the draft tube and the exit of the runner, that is section 2 and section 3, we get the pressure head at section 2 plus kinetic head at pressure 2 plus potential head at section 2 should be equal to the pressure head at section 3 plus kinetic head at section 3 plus potential head at section 3 plus the frictional loss. Now from here to here, now we cannot ignore this as HF, unlike the previous case. Previous case, this distance was less, that's why we ignore it. But now it is a long distance, so we cannot ignore this time. Okay, so HF remains here. Further, HF is given by this expression, okay, difference in kinetic head times a coefficient gives us the frictional loss. Frictional is basically due to flow of liquid, right? That's why we take the kinetic head here. All right, further we can substitute E3 by rho g, or the pressure head at level 3, to be atmospheric head plus the h, right? We can substitute it here, and we can substitute hf is equal to this much, and we get pressure at 2 is equal to atmospheric pressure head minus this parameter. Now what did you notice from this? What you need to notice here is pressure at this point, okay, section 2 is less than atmospheric pressure by a fraction of hf by hf minus v2 square divided by the kinetic head, this parameter, okay. Now if it was same diameter at this point and diameter at this point was same, what will happen? V2 square minus the velocity would have remained same because the area of cross section is same. This parameter would be 0, right? So here the pressure would be P2 by rho g is equal to PA by rho g, atmospheric pressure head, minus HS. So that would be the pressure head. But the cross section is increasing, the velocity head at this portion and this portion is different. So what we can do is we can further reduce the pressure here. That is what we also call by regain, pressure head regain. We know that the principle of reaction turbine works on the pressure difference at inlet and outlet. If we reduce the pressure, more and work can be done, right? That is the concept. More work can be done. So with the help of a draft tube, pressure energy at this point can be reduced by this much. Yes, that's why the shape is conical. Further, one more thing we need to understand is pressure head at this point is more than this point, meaning if it was less, because it is pressure at this point is less, right? If the pressure is less, what would happen is water will simply go up in opposite direction. You know that water flows from higher pressure to lower pressure. Pressure here is less than atmospheric pressure. That is what we have discussed here, right? Here pressure at this point is less than atmospheric pressure. Water here, the pressure is more, so it would go up. But the thing is, because of the draft tube, the pressure here, if you compare this pressure at this point and at this point, pressure here is now at this point is more, right? That's why the water won't go up. So this is the reason, that helps that is the main function of the draft tube. Okay, further, let's try to solve a numerical with this. A conical draft tube of a reaction turbine has a diameter of 1.5 meter and 2 meter at its end. So 1.5 meter and 2 meter. It is set 7 meter above the tail rest level. So from this to this is 7.57 meter. When the discharge from the turbine is 12 meter cube per second, calculate pressure head at the entrance okay, and the efficiency. Assume loss of energy in the draft tube as 0.35 times the velocity head at the runner exit. Atmospheric pressure head is equal to 10.3 meters. So now, since the diameters are given, we can find area 2 and area 3 corresponding to this diameter and this diameter respectively. And once discharge is known, area is known, we can calculate velocity at this point and velocity at this point. Yes. And further, we can also go on calculating velocity head at this point and velocity head at this point. And also one more information is given. The energy loss, which is frictional loss, is 0.3 times, right? So 0.3 times the velocity head at the exit. So this much, that is the frictional head loss. Sorry. Okay, now we have also derived in our previous slide that pressure head at this point is equal to atmospheric pressure times this H. Right now we do not know H, so pressure head we know 10.3 plus H. And next, what we do is we apply the Bernoulli's principle at exit and at level 2, and from here we can calculate the pressure head at this point is this much, and we can simply calculate the efficiency by using the formula that is given in previous slide. In my previous slide, if you have noticed, I have taken this divide by 2g as a LCM and I have took it on top, okay. But in this case, if you keep it like this, since you have already calculated velocity head as 2 points, so it would be easy. You simply substitute the value and you can get the result. Okay, now let's move on with the next topic, that is the surge tank. Now in my first lesson while discussing the turbines, I have also shown you a schematic of a hydropower plant. That time a 4-bay was coming and I said it temporarily stores water, and I also explained that time that sometimes it is also known as surge tank. So here we are using surge tank. The main purpose of the surge tank is when when we close certain control valve somewhere near to powerhouse in the pen stove, what happens is water is flowing at a very high speed here, and suddenly if you close this, all the kinetic energy that was possessed by the liquid gets converted into pressure energy, right? So there is an exponential rise of pressure head in the inside the pipe, which may burst this pipe somewhere where there is a weaker section. So that is dangerous. So what we do is we connect this pipe with the surge tank. So even if there is a closure of valve somewhere here, the excess, because of the excess pressure in the pipe, the water simply flows in against the gravity into the tank. Okay, so that's in the process the pressure is equalized, the pressure is balanced in the system. That's why, and because of this, there is, the piping network may not be damaged. So for that reason a surge tank is used. Okay, so that is the basic principle why surge tank is used, and that is the function of a surge tank. Surge means excessive rise of something, right? So that's why it is also known as surge tank, to reduce the pressure. When you close a valve, pressure increases. To reduce the pressure or equalize the pressure, it is connected to the tank and water simply flows to the tank, whereby the pressure is equalized or normalized. Okay, this is it for the surge tank. And the last topic for the chapter is the runaway speed. It is very straightforward. Okay, now if a turbine works under certain load, okay, that is electrical load. Now suddenly if that load is removed, then the turbine tend to rotate at highest possible speed. So that highest possible speed is known as what that is known as the runaway speed. And for Pelton wheel it is about 1.8 to 9 times normal speed, and for Kaplan it is about 3 times the normal speed. And usually what happens is when the machine starts to rotate like this in a very high speed, it may tend to vibrate. Okay, because of this vibration it may cause other instrument nearby to get, it may damage. So usually the powerhouse and all the equipments are designed for this runaway speed. So that is why the significance of runaway speed is That is the significance of runaway speed. Okay, so whenever we design any component of a hydropower plant, that time we must take into consideration this runaway speed, because at any time if a governor of a system fails and if the turbine rotates at the maximum speed, which is also known as a runaway speed, which may cause damages to the other components. So that's why all the components are designed for this speed. With this, we have come to an end of our chapter on turbine. So next chapter is performance of turbine, but performance of turbine becomes a little bit hard to understand without doing any experiment on turbine. So I do not know whether I should be carrying on, or if if the college reopens, then we have to do the experiment, and along with the experiment, I would like to explain the next chapter, that is performance of a turbine. So I am skipping this performance of turbine because it will not make any sense without doing any experiment on it, because it discusses all the experiment results. Okay, so for next chapter, I'm continuing with pumps, that is centrifugal pump. Okay, guys, thank you. We'll continue our session next time. Thank you.